us look at the questions. What is meant by the term enthalpy change of hydration? So this one is the definitions of enthalpy change of hydration. So this is a 2 marks questions. So let's take a look on how we answer the questions. Okay, so first of all, you have to say it is the enthalpy change when 1 mole of ions. Okay, so we focus on 1 mole of ions. So this is the important keyword, 1 mole of ions. So this one will give you 1 mark. 1 mark. Okay, to get the second mark, you have to say in the gas phase are dissolved in water. So the important words here is the gas phase and water. Okay, so that is how we get 2 marks for this one. Now let us move on. Part 2. Write an equation that represents the delta H hydrations of the magnesium 2 plus ions. So what we can do here is we can just follow the definitions. We start from magnesium 2 plus, the ions in gas phase. So to put the state symbol G, which is gas. Okay, so after that you have to add water. Okay, and after that it becomes magnesium 2 plus aqueous. Okay, so this is the equations that represent hydration. Okay, so the other option is magnesium 2 plus in gas state plus aqueous become magnesium 2 plus aqueous. So this is accepted as well. Now let's move on. The next one, suggest a reason why delta H hydration of the magnesium ion is greater than delta H hydration of the calcium ion. Okay, so we want to understand it in this way. We have to know that the delta H hydration is affected by the charge. Okay, so let me write at the side here. Delta H hydrations is affected by the charge of the ion over radius or size. I put a more general term, size of the ions. Okay, so when I put it in this way, you have to understand that what I put on top is proportional. That means the greater the charge, the greater the enthalpy change of hydration. So when I say the greater the enthalpy change of hydration, that means it is getting more exothermic. Okay, so whereas the size is inversely proportional. So the size who stay at the bottom is inversely proportional with the hydrations. So that means the smaller the size of the ions, the greater the enthalpy change of hydration. So again, when I say the greater the enthalpy change of hydration, that means it is more exothermic. So because of this theory, so we can just answer accordingly. Okay, this is the theory, put in a box. so now let's see how we answer these questions. So we're going to suggest a reason. Okay, suggest a reason. So you may say based on size actually. Okay, so of course no point to talk about the charge because they have the same charge of 2 plus and 2 plus for both magnesium and calcium, so no point to talk about the charge, but it is good to talk about the size of magnesium and calcium. So we have to know that magnesium is smaller than calcium. Okay, so we just state that magnesium 2 plus has a smaller size than calcium. Okay, so that is how we answered it. We just give one reason and make sure that you are writing ions, magnesium 2 plus ions and calcium 2 plus ion. So make sure you are using ion instead of using atoms. So if you write in words, you have to write magnesium ions, but if you write in chemical symbol, this will be fine. Now let's move on to part 4. Suggest why it is impossible to determine the enthalpy change or hydration of the oxide ion. So the reasons why oxide ions cannot use to determine the enthalpy change or hydration is because if you look at the equation that we have in a normal situation, as in here in part 2, magnesium 2 plus in gaseous phase dissolve in water to form magnesium 2 plus aqueous. So oxide cannot do that because basically when oxide dissolve in water, it doesn't form oxide in aqueous because oxide will react with water to form something else which is not oxide aqueous but it is hydroxide. So oxide react with water molecule to form something else which is not oxide aqueous, hence you cannot determine that. So we write our answer in this way. Oxide reacts with water to give hydroxide ions. Okay, so if you don't want to write in this way, even equation is accepted. Okay, so this way or equation. So oxide in gaseous phase plus water become hydroxide in states of oxide aqueous, become hydroxide. So because of that, we could hardly determine the enthalpy change of hydrations. Okay, so let's move on. Part B. Let us look at the question first. The enthalpy change of solution for magnesium's chloride, delta H solutions for magnesium's chloride, is represented by the following equation. So let's see the equation here. Magnesium chloride compound in solid form dissolve in water and they form magnesium 2 plus ions and chloride ions. Okay, so this is the equation that represents the delta H solutions for magnesium chloride. Describe the simple apparatus you could use and the measurements you would make in order to determine a value for delta H solutions of magnesium chloride in the laboratory. So before we write down the answer, so let us talk about the process of doing this. So first of all, you have to prepare a beaker of water. Okay, so a beaker of water, and then you add magnesium chloride inside, magnesium chloride solid inside. Okay, so after that you dissolve it, and then you check the change in the temperature, so after that you have to use Q equal to mc delta T to find out the heat release when you dissolve magnesium chloride. Then you can find out the delta H solution by using Q over mole. The mole here is the mole of magnesium chloride. So because the process is in this way, hence let's see what should we write for the answer. So first of all, you need to know the M here. The M here is the mass of water. Okay, it's the mass of water. Mass of water. Okay, so because of that, we have to mention about the the water that you use over here. So you have to mention about that. Okay, so now let us write down the first point. So the first point, you can say measure the volume of water. Okay, that is the first point. Okay, now the second point. So you can mention okay, now you look at the formula again. Q equal to mc delta T, right? So delta T is the change in temperature. Okay, change in temperature. So because of that, we need to know the, okay, I write down first, change in temperature. Because of that, we need to state the measurements of the initial temperature and the final temperature. We have to state that. So second point, you can write, take the temperature of the water. So this is called the initial T. Okay, initial T. Okay, now let's move on. We look at the formula again. So over here, once you find out your mass of water, initial temperature and final temperature, so final temperature, of course, is the temperature achieved, the highest temperature achieved after you dissolve magnesium chloride. That is the final temperature. So at the meantime, right, after you measure the initial temperature, what to do is you have to add magnesium chloride into the water. So you need to know how much magnesium chloride you are using, because at the end you have to change it to the mole. So we need to know the mass of magnesium chloride. So let's talk about this. So next point, weigh out the mass of magnesium chloride in solid form. Okay, so then you may say additional point like dissolve magnesium chloride. Okay, stir. Okay, now next point. So after you stir, you have to check the thermometer to record down the highest temperature achieved by the solutions. Okay, so now we write down the last point. Take the highest temperature full stop. Now that's all, 4 points only. Okay, 4 points only for this question. So as you can see the question again, describe the simple apparatus you could use and the measurement you would make in order to determine a value for delta H solution. Okay, so we just mentioned what measurement we are taking. So we are taking the volume. We are taking the volume of water. So volume of water can directly converted to the mass of water. Like for example, 200 cm cube means 200 gram. Okay, 200 gram. So that is the first measurement. The second measurement that we are taking is the temperature, the initial temperature. Okay, so the temperature of the water. So this is the second measurement, temperature. The third measurement that we are taking here is the mass of magnesium chloride that dissolve in water. Okay, so of course after that we are going to change it to mole. So next one we are talking about the highest temperature. So I'm going to add one more point here. So final temperature. Okay, so the fourth measurement is the temperature again, which is final temperature. So we are not going to talk about what formula to be used and how you count. Okay, that is too much already. Okay, that will be more for paper 5. So let us move on. Part C. The table below lists data relevant to the formations of magnesium chloride. Okay, so we have the formations of magnesium chloride, solid, okay, solid, and formations of magnesium chloride aqueous. Okay, so let's see the difference between these two. The first one is magnesium solid plus chlorine gas become magnesium chloride solid. The second one is magnesium solid plus chlorine gas become magnesium chloride aqueous. So we have to know that the first one, there are formations. These two are formation actually. So no matter the first one or the second one, we always start with reactants in the standard state. So you know magnesium in standard condition is a solid. So that's why you can see both of these equations start off with magnesium solid, because in room condition magnesium exists as solid. Chlorine start off with chlorine gas, because in room conditions chlorine exists as gas. But the product, right, it depends on the questions. So it must be 1 mole of compound. So for the first case, magnesium chloride 1 mole in solid state, because the question mentioned that magnesium chloride in solid. But for the second equation, magnesium chloride in aqueous, 1 mole of magnesium chloride. So here right hand side must be 1 mole. Okay, make sure you stick to that. That is the definitions of enthalpy change of formation. Must form 1 mole of compound. Now lattice energy of magnesium chloride, that give this value. So what is lattice energy? So let's take a quick revision on this. So we have to know that lattice energy here is the ions in gaseous phase, magnesium's ions and chloride ions in gaseous phase, they combine to form magnesium's chloride solid. And that is lattice energy. So lattice energy is released when this reaction happens. And now hydrations. Hydrations, you have to remember one thing. When we count out the enthalpy change of hydration, we count separately. I mean, for magnesium's 2 plus, the positive ion, there is a value for the positive ion. For negative ion, there is another value. Okay, there is another value. Okay, so which means this is the magnesium 2 plus gaseous ion plus aqueous become magnesium 2 plus aqueous. Okay, so which means they give us the hydration of positive ion. They don't give us the hydrations of negative ions. Okay, so let's continue with the question again. Okay, so by constructing relevant thermochemical cycles, use the above data to calculate a value for the enthalpy change of solutions for magnesium chloride solid. Okay, so enthalpy change of solution is slightly different from enthalpy change of hydration. For hydration, they give separated value for positive ion and negative ions. But for solutions, there is only one value for positive ion and negative ion. Only one value, you know. So which means this is 2 in 1. This is 2 in 1. But this one, 2 separated value. Okay, so we have to make ourselves clear on this. Okay, so magnesium's chloride, the whole thing, let's say I write down the equation here. Okay, so for example, magnesium's chloride, magnesium 2 plus aqueous plus chloride aqueous. So only one value. Only one value for the enthalpy change of solution. Only one value. Okay, not like this. You see hydrations. Okay, let us talk about hydration again. Hydration, this is the delta H hydration for Mg2 plus. Okay, so we should expect chloride plus aqueous become chloride aqueous. So there you have another delta H hydrations for chloride. Okay, 2 separated values. But this one, for delta H solution, it is one value that represents the positive and the negative ions. Okay, so be careful with that. Now, how to do these questions? Okay, so we have to know that the question 1, a thermodynamic cycle. So we have to make use of the information here to work it out. Okay, so we have formations. Okay, we have formations, enthalpy change of formation, we have lattice energy. So we just use the common way to start the question. So the common way to start the question is whatever they ask, the solution, enthalpy change of solution, we just put it on top. Okay, so we write an equation in this way. Magnesium's chloride solid, delta H solution. We are going to find this, so it is unknown at this moment. I call it X. So the product are magnesium 2 plus aqueous plus chloride, 2 chloride aqueous. Okay, So this is the equation that represent the solutions of magnesium chloride. So we make use of the information available over here. So we have formations. So as you can see, the equation that I put on the right hand side, so we can make use of the element in room conditions to form magnesium chloride. So I'm going to put it down here, and then I will make an arrow to magnesium chloride solid. Okay, so that means I'm going to use the enthalpy change of formation to build up the thermodynamic cycle. So magnesium solid plus chlorine gas. So they are forming magnesium chloride solid, and the value involved is minus 641. Okay, now I can use the second information here, the formations of magnesium chloride aqueous, so which is this equation. Okay, so I'm going to start from the elements, and I'm going to form magnesium chloride in aqueous, which is this at the same time. Okay, so it's the same thing. So which means I'm going to put an arrow here from the element in room conditions to ions in aqueous. So that is the formations of magnesium chloride aqueous. So the value involved here is minus 801. Okay, so now in order to find X, so we have to use Hess law. So according to Hess law, you want to form a particular product, you either do it directly, which is X, okay, or you can also do it indirectly, where you do it in two steps. For example, from magnesium chloride solid, you change to element, for example. So you have to go down, and after you go down, then you go up again to form the product. So you use two steps to form the product. The enthalpy involved will be the same as you use one step to form the product. Okay, so same enthalpy. So that's why our equation here can be equal to the two steps. This is the one step enthalpy change. Okay, this is the one step enthalpy change is equal to the two steps enthalpy change. So like what I said, I have to go down. So when you go down, you have to change sign. So it becomes positive 641. So after that, I have to go up again to get the final product. So going up means I can take negative 801. Okay, negative 801 without changing the arrow. So I can just follow back the original value. Don't need to change sign. We change sign when we need to do it in the opposite way compared to the arrow that we have. Okay, so by doing so, we can just calculate this by using calculator, and at the end, if we get negative 160 kilojoule per mole, and we fill out the answer over here. Okay, so now let's move on. So we have done the first part. Now the second part, we have to look for the enthalpy change of hydrations of chloride alone. So again, we need to build a thermodynamic cycle. So what kind of cycle are we going to use? Okay, actually we can start off with solution again. Okay, we start off with solution again. So magnesium chloride solid, the delta H solution is negative 160 from what we found. So magnesium 2 plus aqueous plus 2 chloride aqueous. So now our thermodynamic cycle must involve hydrations. Okay, must involve hydration. So bear in mind that let's see the equation that I put over here. Okay, hydration is basically the gaseous ion dissolved in water to form aqueous ion in aqueous, So what am I going to do is I'm going to put my gaseous ion down here. Gaseous ion, I'm going to put down there, and then I'm going to connect arrow. Okay, so the magnesium's gaseous ion form magnesium aqueous ion. So this one is given as the delta H hydration, which is minus 1890. Okay, so how about the gaseous ions of chloride to aqueous ions of chloride? So this is the unknown that we have to work it out. Okay, the unknown. At the same time, remember the definitions of hydration is to form 1 mole of aqueous ions. Okay, aqueous ion. But now, if you see here, we have 2 chloride. Okay, 2 chloride here. So when there are 2 chloride, 2 mole of chloride, so that means we have to the enthalpy change involved will be 2 times of the enthalpy change of hydration is 2 times. Okay, so which is 2 delta H hydration, or in other words I call it 2Y to make it simple. I call it 2Y. We are looking for Y actually. So our thermodynamic cycle is not complete in this situation. So we need to build up 1 more arrow to join up between the gaseous ion and the solid, the magnesium chloride in solid. So that is, if you can see here, it is the lattice energy. So where the gaseous ion combine and form solid. So I can put an arrow from here to here. Okay, I can put an arrow. So in this particular way, and the energy involved is the lattice energy of magnesium chloride, which is minus 2526. Okay, so in order to count the Y, we can use Hess law again. Like what I said, you can change your reactants to product. Okay, you can change your reactant to product in 1 step. The energy involved is minus 160. This is 1 step to get the product, and at the meantime, the enthalpy change involved in doing it in 1 step is equal to enthalpy change involved in doing it in many steps. So which means now you can also do it in 2 steps. You change magnesium chloride solid to gaseous ion first. This is 1 step. Then second step, you change it to aqueous. Okay, so the energy involved is the same. So that's why we can put equal to. Okay, go down first, change sign. When you go down, it is opposing the direction of the arrow, so we have to change sign. So that is going to be positive 2526. And now we have to do the second step by going up. Going up is not against the arrow, it's just following the arrow. So we are not going to change sign, we just take the value here straight away. So the first value, negative 1890 plus 2y. Okay, so we have to solve this equation and finding out the y. So that is going to be negative 398. Okay, negative 398. So y is equal to negative 398 kilojoule per mole. So let us move on to the last part. Describe and explain how the solubility of magnesium sulfate compares to that of barium sulfate. Okay, so in order to answer these questions for A2 chemistry, they expect you to explain solubility based on the lattice energy and the hydration's enthalpy change. Okay, so which means you can refer to these part 2. Okay, refer to part 2 here, the thermodynamic cycle here, and try to get some general formula for delta H solution. Okay, so now I'm trying to explain it by using this thermodynamic cycle. So I'm going to put it in different color. This is not part of the answer, it's just explanation. Okay, so I'm going to put it down here. Okay, so first of all, you can see that on top of the equation, that is delta H solution. Okay, so I form an equation first. Delta H solution is equal to, okay, that is the one steps, the one steps reactions to get the product, and we can also do it in 2 steps, okay, like what we discussed just now, but the lattice energy have to go in the opposite way. So in general, I'm going to put it in this way. So I'm going to put negative of delta H lattice because I have to oppose the arrow. Okay, now come to the other side. The other side is the hydration. Like what I said, for hydration, positive ions and negative ion has their individual value separated. Okay, individual value. So in general, I can just write it out in this way: plus delta H hydration for the cation ions. I just put it in general, plus delta H hydration of the anion. So our explanations on solubility is based on this general equation. Okay, it's based on this general equation. So now let's look at the general knowledge on this enthalpy change of solution. Okay, enthalpy change of solution. So if let's say the enthalpy change of solution is very exothermic or slightly endothermic, then the compound is soluble. Okay, so the second situation is if the enthalpy change of solution is endothermic, then it is insoluble. Okay, insoluble. So of course you have to know about what is meant by slightly endothermic and what is endothermic. Slightly endothermic is like maybe 1 digit in value. For example, like sodium chloride. Sodium chloride, the enthalpy change of solution is positive 6 kilojoule per mole and it is soluble. It is just 1 digit. Okay, so let's say if the endothermic here is like maybe 2 digit onward. Okay, like for example like 20 something or 30 something or maybe 3 digits like 100 something, so that is insoluble. Okay, so that is the difference between slightly endothermic, which is 1 digit in kilojoule per mole, and endothermic here is 2 digits, 3 digits, and so on in kilojoule per mole. Then it is insoluble. Okay, so to know whether the delta H solution is exothermic, slightly exothermic, or endothermic, it depends on the lattice energy and the hydration's enthalpy change. Okay, so you have to know that lattice energy is always exothermic. It's always exothermic. So hydrations, likewise, they are also always exothermic. Okay, so because of a negative in front, so it will change this first term to become a positive value. Okay, to become a positive value. Okay, why it become a positive value? Just imagine, like what I said just now, lattice energy is always exothermic, and hence it is a negative value. Okay, it's a negative value, and because of another negative, so this term become a positive term. Okay, whereas the other two terms at the back, the hydration, so the hydration is always negative. Okay, it's always negative and negative. Okay, so now it means what? It means the lattice energy will make the solubility become more and more endothermic, but the hydrations will make the solubility become more exothermic. So because it is negative, so it will make the solubility become more exothermic. So in general, it is like that. So now let's come back to the questions. We look at the answer, and at the meantime, I will explain it based on these equations. So first of all, what are we going to write is we just state between magnesium sulfate and barium sulfate who is more insoluble or who is more soluble. So we can say it in this way. So we can say that first point, magnesium sulfate is more soluble than barium sulfate. Okay, so this is the first point. Okay, so beside this, you can also say, okay, you can also say the reasons why this is like that. Okay, so you can say because the enthalpy change of solutions of magnesium sulfate is more exothermic than barium sulfate. Okay, this is the second point. Then for the third point, you can further explain it by saying that going down the group, you can say barium 2 plus has larger ionic radius than Mg2 plus. Okay, so that means their size, the size of barium 2 plus is greater than the size of Mg2 plus. Okay, so now why we have to talk about the size? Because no matter lattice energy or hydrations, it is affected inversely by the size. Okay, so you have to know that. Okay, I put a star here. Lattice energy is proportional to charge over size. Likewise, hydration energy is also proportional to charge over size. Okay, so when the size is getting bigger, then the delta H lattice is getting smaller. Okay, be careful when I use getting smaller here. Getting smaller means smaller in magnitude. Getting smaller in magnitude. So for example, let's say you see magnesium 2 plus. Magnesium 2 plus, magnesium's chloride is minus 2526. So when it comes to barium chloride, maybe minus a few hundred. They are getting smaller. Yeah, they are getting smaller in terms of magnitude. Don't care about the negative. So don't care about the negative. So the value is getting smaller. The value is getting smaller from maybe 2000, negative 2000 to maybe negative few hundred. Okay, that is less exothermic. Getting less exothermic. Okay, so let's move on. As you can see here, for enthalpy change of hydration, it is also affected by charge over size. So the same situation happen. When the size increase, the delta H lattice decrease, become less exothermic. You have to know that the delta H hydrations for the cation is also decreasing. So which means become less exothermic. Of course, why cation? Because there is a change from magnesium to barium for cation, but for anions there is no change at all because they are using sulfate. Okay, no matter magnesiums or barium, they are using sulfate as the anion, magnesium sulfate or barium sulfate. So there is no change for the anion. So we just don't care about the anion here. It's a constant. So maybe I write here, this is a constant. Okay, the anion enthalpy change of hydration is a constant. Okay, so now let's move on to the next point. So that's why we have to talk about the radius as the third point here. Now the fourth point, we said leading to smaller lattice energy, or you can say less exothermic. If you don't want to say smaller, you can say less exothermic. And smaller enthalpy change of hydration. This is also less exothermic. Okay, so next point. This is the fourth point already. Now, okay, of course you can see there are only 4 marks. But we have more explanations on this. So the fifth point, I put it down here. there is a difference. This is very important. There is a difference between the decrease of lattice energy and the decrease of enthalpy change or hydration. Okay, there is a difference. So you have to say that the fifth point, but decrease in delta H hydration, decrease in delta H hydrations of the cation is greater than the decrease in lattice energy. Okay, so these are the 5 points that are required. The last point may be a bit more confusing. So here, I'm going to put some explanation on the last point. Okay, so decrease in hydration energy for the cation is greater. So how can that happen? So you know, hydrations have something special, like what I said before that. It has individual value for cation and anion. So why there is a big decrease in hydration energy? Because if you look at cation alone, magnesium 2 plus to barium 2 plus, that it involves a very big change in size. So how we know that? You can look at periodic table as your reference. If you just look at the relative atomic mass alone, we can roughly figure out that magnesium 2 plus 24.3, barium 2 plus 137.3. So if you look at cation alone, you will feel like the mass increased by about 6 times. Okay, by about 6 times. Okay, so and let's say we assume that it is proportional between the mass and the volume or the size. So the size we should expect to increase by around 6 times. Okay, is increased by around 6 times. So because of that, now you look at the formula. If this is getting 6 times greater, then this is going to be 6 times smaller. Okay, 6 times smaller. Okay, so hydration, when you go down the group from magnesium to barium, it is going to be roughly 6 times smaller. 6 times smaller. So which means decrease a lot. So the decrease in hydration is a lot. However, for lattice energy, the decrease is very much lesser, because lattice energy involve both the magnesium sulfate and the barium sulfate. So if you can see here, magnesium sulfate, the mass, okay, if I count it out in terms of mass, we understand it through its mass because we can count it easily. Magnesium sulfate, the mass is, okay, I just total up straight away for you. The mass is 120.4. Barium sulfate, the mass is 1 233.4. Okay, so if you see the change it's in mass, it is like 2 times increase. So because of that, you look at the formula here. So if the size increased by 2 times, the lattice energy, we should expect it to decrease by 2 times. So because of that, the decrease in hydration energy is very much greater, whereas the decrease in hydration is very much smaller. Okay, so let's come back to the formula here. Okay, so for hydrations, as I said before, it makes solubility become more negative. So because of a very big decrease in hydration, so because of a very big decrease in delta H hydration, so this term is getting not so significant already. Okay, not so significant. Okay, so not so significant, not affecting this so much already because it decreased a lot already. Okay, so not affecting this that much already. But this one remained very big, you know. So you just divide by 2, imagine, just divide by 2, it still remain a very big value. So because of that, it is still a very big positive number over here. So a very big positive number minus with a very small negative number, okay, because you divide by 6 already, it become very small already. So it's something like, just imagine you take a value, let's say this remain very positive, so let's say positive 1000, you minus with a very small value, let's say minus 5. So of course at the end you get a very positive answer. Okay, you get a very positive answer. Very positive answer means insoluble, and because of that, barium sulfate is insoluble. Okay, because this one become more significant. Okay, it's endothermic. The positive value become more significant, the negative one is getting very small and less significant. So big positive number minus small positive number end up with a very endothermic answer, which is insoluble. That is what happened to barium sulfate. Mathematically it is like that, but when you write, we just write in a simple way. Decrease in hydration, so cation ion is greater than the decrease in lattice energy. So the explanation at the back is not expected to be explained. Okay, so we don't explain it based on the equation, just write this statement and you will get 1 mark. Okay, so that's all for this question. Thank you.